Welcome to the quadratic function. This is going to be a lot of fun. Have a look around the screen here. What do you think the quadratic function's graph looks like? Hey, there's one. Oh, here's a useful one. Don't know what's going on there. Here's a bridge with one. And, oh, the McDonald's sign got two of them. And upside down or whatever. We don't know which way around this quadratic function goes when you draw the graph of a quadratic function. And I wonder if you like to look at the name up there, quad. That might mislead you. We're going to investigate all these things. But first of all, why the quadratic function? Well, I guess let's come over here to this example. Do you know what this is representing? This is a headlight of a car or some other vehicle. And what we've got is a globe here. And there's generally a shield around the front, so from the globe there isn't emanating direct rays here of light, because that wouldn't give uniform illumination. So actually we shield it, bounce the rays back, and then they come out parallel. This is a property of this type of shape. Okay, if you have a source at this point in the middle and bounce the rays backwards, you get parallel rays coming out here, parallel beams, and this gives more uniform illumination. I wondered if you've ever looked at car lights and how they're set up. But that's an application. And of course we could do it in reverse. Okay, if we had beams coming in, and parabolic reflecting telescopes do this. I think I've just told you something there about the shape, but we'll come to that later. As the beams come in, they will also come to a focal point this way, so you can actually intensify the incoming signals. And telescopes and satellite dishes producing these incoming beams of various frequencies can be concentrated at this point. It's called the focal point. Okay, so it works both ways. That's a very important application of this function. And of course, come down here to our bridge. We've got some strengthening going on here due to this particular quadratic function here, and this particular shape that it produces when we graph it. This is a sort of a flatter one, and it's sort of upside down, and this one's on its side, whatever. I don't know, what's the shape supposed to look like for this quadratic function? And here we've got a couple over here in the McDonald's sign, and they're upside down and next to each other. Well, what sort of function gives this shape? It looks like it's got some interesting properties that are used in the world in a practical way. So this is exciting to investigate something like this. So come down, let's investigate the simplest function that I've been able to find that has this sort of shape. Well, there it is. Okay, and what have I done down here? Hey, look at this. What I've done is said, well, let's examine this curvy shape. Let's go to -4 over here and look at what the y value is at -4, and it comes to 16. I'm a bit off there. And if I go to -3 and go up, the y value is 9. I've done that for all these values along here. -4 mapped onto 16, -3 to 9, -2 to 4. What is the connection here between the dependent variable y and the independent variable x? What's the formula? What do you do to x to produce y? That's the rule for a formula or equation of a line, isn't it? Y equals some function in x. And this function tells us what to do to x to produce y, so that all the points would line up on that particular shape. Okay, that's the definition of a formula for function. The rule that all the points x and y must obey to all line up. What is the rule? Can you see it? What do you do to x to produce y down here? What's happening every time? What do you do to x to produce y? Well, you might pause the presentation and think about that. I'm going to give you the answer now, though. can you see that y equals the square of x? There's our parent quadratic function, the first one that we've ever found to give this particular curvy shape. And this shape is very useful, as we saw above, in the world today. Okay, so let's go further with this and say, well, why would it be called a quadratic function? Because I guess you thought quadratic, hey, quad means four usually, quadruple. If you're into rowing, a quad scull, four people in a boat. Hey, well, how come we've got x squared? What's going on there? Okay, let's have a look over here. Screen clippings here, this time from Pearson's, and let's have a look at this word quadratic. Comes from the Latin word quadratus, that means four-sided. So it's still in this four business. What's going on here? Or, oh, here it is, four-sided, or to make a square, or simply a square. Okay, so the four-sided thing, therefore, is to do with the geometric shape of a square. Okay, numerus quadratus means a square number. This is going back to the old days now. In a Latin word. Before modern algebraic notation, the 17th, 18th centuries, this geometric figure of a square was used to indicate a number multiplying itself. Aha. So that was the symbol to represent the fact that a number was multiplying by itself. I don't know, is that directly related to finding the area of that? Is that the connection? Anyway, raising a number to the power of 2, right, so that's like x squared, in modern notation is commonly referred to as the operation of squaring. Okay, so that power of 2 is connected to a square. It's squaring, which gives you this, which gives you the old word of quadratus, four-sided. Hey, that's an interesting journey. I would have thought, as you probably did, a quadratic function would have some fours or something in it. But it hasn't. It's got x squared. Interesting history here. So quadratic then became associated with a polynomial of degree 2 rather than associated with 4, as the prefix quad often indicates, quadruple. So we got sucked in a bit there. Okay, but what's this word here? Polynomial. Hey, this is an interesting one, because the quadratic function is an important, first function in the world of polynomials in mathematics. So let's have a look at polynomial. Okay, going back to the Latin again, poly means many. We've got polymers and things like that. And nomial means number. So we've got polynomial, many numbers. Oh yes, what are they saying? Well, you've got x squared. Maybe in the same function you could have a 2x and a constant. Okay, so that could be a quadratic. Our simple mummy or daddy of them all come up the top here is this one. Y equals x squared. But we could make some others from this one by adding on a number, a coefficient, times x to the 1 and then a constant. And then we would have a quadratic, because it's got the highest power is 2, but we have many powers. We've got 2 and a 1 and x to the 0 if you like. X to the 0 is 1, isn't it, from your index rules? Okay, so we're on a big journey, because what are you going to ask? You're going to say, well, what's the next polynomial? Well, it could be x cubed plus, I don't know, x squared plus 3x plus 2. And the journey's going to begin. How exciting is that? So we're going to concentrate in this section of the course on just with this quadratic here. And later on in mathematics, you'll learn how that can grow. We can develop that into higher powered polynomials. And this one is actually called a cubic. And that polynomial work in mathematics is very important. Okay, so let's go on and just define what we've just said there now. And here we are, this definition here. A quadratic function is a relationship between two variables which can be written in that form. Okay, remember, a function is always some relationship telling you, if you like, I'd like you to have the interpretation of the function statement being the connection that we need to make between the x and y of any point on the curve or on the shape, on the graph, so that we will always get it lining up. Okay, making that symmetrical curve there. We're starting to see some interesting properties. And the rule for this one is if a point's going to lie on there, what must its y be? Its y must be the perfect square of its x value. And then it will form this very nice symmetrical shape. Hey, we need a name for this shape, don't we? I think we'd better give it a name. Well, it's already been done, mate. Anyway, we'll come down below and have a look. So we're going to say A, B and C are constants. We go to no x's in there, and A is not equal to naught. Why is that? If A was equal to naught, you'd have naught x squared plus bx plus c. Wipe out. Oh, that's a straight line. So obviously, when you say it's ax squared plus bx plus c, we must have the proviso that the a is not naught, because otherwise the quadratic function becomes a straight line. Okay, are you getting the hang of this now? This is moving on pretty quickly from just looking at a couple of shapes that we see in practice in the real world. We're now getting into some math, mate. Let's get into it now. Here we go. Now, this is a bridge type quadratic function. Well, what do you mean a bridge type? Well, can you see we've got the roadway there, or the the roadway is supported by this shape, which is a quadratic function. This one's upside down. I don't know what its formula would be, but y equals x squared was the other way up. We might have to work on how do you turn them upside down so you can make this bridge. But if you were designing this, you'd want to know the formula for that function, wouldn't you? To try and create this shape, and to therefore work out all the positions of these supports here and where it's going to end up on the end. So maths to the rescue in engineering. Engineering does not exist without mathematics. So let's keep going. Hey, I wonder if this shape upside down here could give us a possible name for the shape or the curve. And what the Greeks said was, gee, that looks like what happens when you throw a projectile. When you throw something up, due to gravity, what comes up must come down, and it comes down in a symmetrical fashion, doesn't it? Unless you turn off gravity, mate, and then it might just keep flying. But anyway, while gravity is turned on, hey, what goes up comes down in exactly the same way, under that same gravitational force. And so what the Greeks said, hey, this looks like something that's been thrown. And the Greek word there is parabola for thrown. It's a parabola. Now be careful here, it's not a parabola. You've got to run all the words together. Parabola, parabola. Okay, so don't break it in the middle. It's not parabola. It's parabola. Okay, so from the Greek meaning thrown, because they saw this shape very common in the upside down way, like this one here, as something that happened every time things were thrown or projectiles were fired. And of course, back in those days, quite a few projectiles being fired, weren't there, in that part of Greek history. All right, so let's go. What have we got? Well, we've got a formula for the shape. Come back up here, and there it is. And we're going to call that shape a parabola. Okay, and now we want to investigate how to make them of different sizes. And I don't know, are you ever going to be able to put one on its side like that to make your headlight beam? I don't know, are you going to be able to do that? We'll have to work on that one. Okay, so we want to build up to say, hey, we can do some useful mathematics here to create shapes that are useful in everyday life. Okay, come down now, and I want to take you on a journey. Okay, I wonder how much you know about your Casio 9860 Plus calculator. Okay, and I'm going to restrict this presentation to just this calculator, and other calculators will have a similar sort of function I'm asking you to use here. So if you turn the dude on and then come up with this screen, the menu screen, can you see I've highlighted here Dyna? Okay, Dyna stands for dynamic, so I want you to go scroll around the screen with this button until that is lit up there, and then hit execute. And you get a window very, very similar to the ordinary function window, but it's dynamic function y equals. What does that mean? Well, what it means is we can introduce another variable. Usually in functions we have y, which is the dependent variable. Alright, that's one variable in our function, the dependent variable, and we have x, which is the independent variable. Okay, so we think about travelling along a curve by changing x and looking at how y is dependent upon it. So y equals x squared is the dependence of y on x for our quadratic function. Okay, but what about introducing another variable? Could we do that? Let's have a look at what this function on the calculator will do for us. Here it is. What we've got here, we'll just get rid of that up here and come down a bit now. Okay, so here, oh, what have I done? What have I done? Look at this. I've put an a in front of x squared there. A, so that's our dynamic variable. That's the one we're going to change in a dynamic way. What does that mean? It's going to keep changing it over and over, not just sit there. It's going to change the value in front of x squared according to what we tell it, and we're going to see what effect that has on the graph of y equals x squared. So how do we work with that then? Well, first of all, how do I get the a in there? How do I get that a in there? Okay, so what I have to do here is go to the alpha key up here, alpha for alphanumeric, alphabet character, alpha, and then there's the a in there. So it's alpha and the x theta t button there to get a in front, and then x squared. So can you enter that in your calculator, y equals ax squared? Now what we need to do, once we've done that, we've introduced another variable. And so we have to explore that. So there's var, so I want you to hit in there F4, and you'll come up with this screen. We're going to now define what values we want a to take as we change it there. So we come up with this screen, and we won't do anything with that for the minute. We want to set it. So set it is F2 in there, and we come up with this screen. I want you to enter by moving this highlight bar up and down with this button. We want to start at 1, go to 5, and in steps of 1. What does that mean? It's going to say, it'll flash on the screen y equals 1x squared, then 2x squared, 3x squared, 4x squared, and 5x squared. And all dynamically, all moving. So you don't go to sleep, mate. Right, okay, very good. Hope you got that. Alright, so down here, let's have a look. If we hit execute, we're back to this window, and shall we look at the speed? To change the speed, we'll choose F3, so look in there at F3, and we get these options here now. The speed. Now, the normal usual speed is this one here, so that's what I've selected. So that's this one, so you hit F3, but you might want stop and go. You can play around with this, good fun. And then if we hit execute, we're back to this window here, and if you hit execute again, you'll get this dynamic movement. But before you do that, I've popped something in here. It might be worthwhile just to make sure your calculator's set up so you can see the window. So if you hit shift and F3 in there, you get view window. Just remember that. So I've chosen to go with the initial view window, which is F1, hitting F1, just before I do hit that execute. Because otherwise, if somebody else has been using it, you've been using it for some other functions, you might not have a good view window. So initial we'll do as a view window here. Alright, so if you hit execute now, what will you get? Well, I've stopped it because To do screen clippings, of course, it captures the screen at one place. And I've captured this at y equals 2x squared. And of course the next one will be 3x squared and 4x squared. We've told it to go through and change that dynamic variable by steps of 1 each time. And what I want you to do is to study the effect of that A in that position on the graph. What are we doing now? What are we doing? We're trying to work with the quadratic function and its formula to see if we can create the shapes that might be useful in our everyday world to create some particularly useful functions. Okay, let's go down and have a look at what I want you to do now. Here's your work. So you're going to have to pause the presentation and play around quite a bit here. Can you see what I've done here? I've brought in y equals ax squared, so that's your first one. And then the next one I put x squared plus a. And the next one, x take a in brackets all squared. So they're the three changes I want you to make to the parent function, y equals x squared. And I want you to learn and investigate what the numbers in those different positions, what effect they have on the graph of the function. Just notice, in the way I've got this one here, it's just this one here, see that highlight in there? If I hit execute now, then I will be working through with that one. So don't forget to change your variable. Probably 1 to 5 would be good for the first ones of each of these. And remember, the one that is highlighted here is the one that you'll be looking at. So maybe just enter them one at a time. But they are the three I want you to investigate. Okay. I think that's all. You might, before you try to answer the questions here, I want you to be pretty ingenious here as a young mathematician. And when we say over here, A affects the what of the graph, make sure you've investigated a nice range of A's. I just suggested you start at A as 1 and go to 5. But what about the effect of any negative A's? Negative A values. Negative A. What does that do? What about fractions for A? What does that do? Can you investigate that in all these positions? Right? These are the three functions or function types that I'd like you to investigate. What are we doing? We're saying we're going to understand the quadratic and all the functions coming from it, or the transformations of it. That's another way of talking about it. We're going to take this function up here and we're going to work with transformations of it. What's a transformation? Oh, well, I don't know, this is a bit embarrassing for me, because a few people said to me once, "Hey, Huddy, your face needs a transformation, mate." Oh, well. Yeah, well, I couldn't afford that. But it means a change, doesn't it? It means moving some points. Maybe something to do with my nose, I don't know. Anyway, moving some points around on the plane. That's what we're doing here. And we're trying to say, if you put A in various positions in this formula, what effect, what changes, what movement of the points on the plane does this produce? All right, this will take you some time. I want you to think carefully about some good statements in here. Some good statements in there. All right, so pause the presentation and have some fun. And then I've got some really interesting challenge for you coming up. Okay. Right, away we go. I hope you had a good time with that. And what we've got here now is this one. Now, just so you can check your work later on, you're going to have to come back to the quadratic function part 2 to find out whether you got the answers right for those transformations. But your homework is, have a look at this. This is a McDonald's sign. Now, are you aware that if people are going to produce over and over the same shape, exactly the same, I can't draw it the same every time, can I? It's a bit wonky. They're never the same. Are you aware that of an area in design called computer aided design? Are you aware of that? Computer aided design, CAD. I don't know whether you've seen that. You know, particularly, let's say, where did it emanate from originally? Back in the 1950s, 40s to 60s, I think, somewhere around there. There were some design engineers in Europe, and one of them was called Bezier, and he was able to design or create functions using polynomials, actually, that would always produce a particular shape. And this is important if you're going to produce designs that are always the same. And so he used a computer program based on formulas for polynomials, a bit more complicated than quadratics, to do that. But hey, you can make your first start in the world of CAD by what? Well, I want you to design this. Ho-ho! How good are you? I don't know. I want you to be able to draw on a grid somewhere a McDonald's sign. Okay, using parabolas. I hope it's better than that one, mate. That's a bit wonky there. Okay, so that's your homework. Now I'm going to give you a few little technical tips here on how you might do this, but this is exciting. You will, with your calculator, which is a mini sort of computer, I guess, be able to put in formulas and create this, and that could be transferred then to a computer, couldn't it? So you are now a CAD designer. Hey, how exciting. Let's come down and have a look at some tips I want to give you. Now obviously, this McDonald's sign is not going to be dynamic. We want a set sign, and so I want you to go back to the graph mode on your calculator, and you can see here all your AX squareds will be sitting there, because the graph function and the dyna function on the calculator share this window. Okay, so you need to delete all of those, because in graph function it can't handle the extra variable. So you want to go to delete here, F2, and delete all of them. So we get this window ready for your functions to be put in these holes, which are going to give you your two parabolas, aren't they? The two parabolas. Oh, that was a better one. The two parabolas. Now, are you up for the challenge? All right. So, clear the window. You're in graph mode now. And let's come down. I want to show you something that might be useful to you. Don't know whether you've ever seen this before. First of all, I've suggested neg x squared. I wonder why. Did you get that already? I'm telling you the answers to the previous one now. Neg x squared. Okay, so you might want that, because I think that's what's going to do that to the parabola, isn't it? And then here, have you seen these before? When you put these brackets in, okay, you can designate the range of x values that you'll see the graph for. So this is saying, draw the graph of y equals neg x squared from the limit of neg 1 up to 1. Okay, so it's going to restrict the window. That enables you to cut off the parabola, because otherwise it'll keep going down. Down, down, down. And you want to stop it somewhere, like there. So you stop your McDonald's sign, and so this is a way of doing it. So let's come down and look at how you do that. So where's the comma? There's the comma. And there's the left-hand bracket. There's the right-hand bracket. Okay, so it's Shift plus and Shift minus key to set up that little interval there. And I'll show you what happens now when you do that. There it is there. Now, I don't think I want the axis through the middle of my McDonald's sign, so I'm going to have to move that around. I'm going to have to have a transformation of that function to move it somewhere. I don't know, do you want to put it up here? Or do you want to put it right on the axis? Don't know where you want to put it. That's your choice as your first foray into computer-aided design. How exciting. Okay, but see here how if I didn't put that, the function would keep going. So I've chopped it off there and there. I don't know whether that's a bit flat, that one, for a McDonald's sign. They're actually quite steep, aren't they? Like that. Okay, so could you do that? Can you change that as well, the steepness of the graph? So I hope you did those exercises earlier, because you'll need those skills now to construct this McDonald's sign. And I reckon you should have a class competition and vote on which one's the best. Anyway, that's just my idea. Well, have you enjoyed it? I hope you enjoy making up your McDonald's sign. Spend a bit of time, think about how you change the function, talk to other people about it, and have fun. I'll catch you in part 2. Cheers for now.